Hello everyone. Let's solve second question from today's weekly contest, that is apply operations to make sum of array greater than or equal to k. So in this question you're given a positive integer k and initially you are also given an array called nums in which there is only one element equal to 1. Okay. Now what you can do is you can perform any of the following operations on the array any number of times. Alright, so you can perform these two operations on the array, right? So first operation is that you can choose any element of the array, increase its value by 1, or you can duplicate any element in the array and add it to the end of the array. And you need to return the minimum number of operations required to make the sum of elements of the final array greater than or equal to k, right, which is given to you. All right, so let us see using the first example only. We are given this 11 is equal to k, and initially we are being given this nums array which only contains an element which is equal to 1. Okay, and I want to perform operations. Now what are the operation? Increment value by 1, right? Or either I can choose to duplicate the value and add it to the array, right? So if we like, obviously you can see that if I keep adding 1 to this only this particular element, right, 10 times, so I will get 11, right? So 10 is also an answer, but I want to return the minimum number of operations. So I also have the option to duplicate the element. So here, if you can try out different combinations, but the best answer you will get is by having this array. So in this array, what you did was you performed three operations on one and incremented its value by 1, right? So you made it 4, and then you used this operation and duplicated this value twice. That is, you did two operations here. So three operations here, two operations here gives you five operations. So this, see, optimally, this is what you have to do, and using doing this only, you're going to get minimum number of operations. All right, you can try out different combinations, you can try out and have different arrays, right, made different manipulations to nums, but you would get the minimum number of operations only when you would consider this array and you would consider the operations that I just told you. All right, so I hope the question is clear what we want to do, right? See, what we want to compare is the sum of this array and this k, right? So what should happen is this sum should become greater than equal to k. So those number of operations we have to do up to we like come to this, arrive this condition, right? And we have to return. So obviously for this, it is going to be 5. Now, from like, so apparently it seems that we have to use dp here, right? It seems that we have to use dp here because obviously what we can do is we are given two choices, right? So what I can do is I can have this nums, right? And what I can do is I can keep performing these two things, right? So why dp? Let me show you. See, we have initially nums, okay, we have one, right? Let me take this as num, and let me take a sum variable also. Sum is going to be 1 initially. Now I can perform these two operations. All right, so I have two choices. First choice is I can choose to increment num by 1. So if I do that, my num will become equal to what? 2, and my sum will become equal to 1 plus 1, that is 2 also. And the other choice that I have is that I can duplicate this 1, right? So I can have num is equal to 1 only, but after duplicating, my sum will become 1 plus 1, which is 2. All right, and then for each of these, right, each of these would have some recursive calls, and if you like draw this recursion tree, you will be able to notice that there are overlapping subproblems, so that hints you to use dp. But if you see the constraint, right, if you see the constraint, it's given to you as this, right? This is the constraint, that is k is less than equal to 10 raised power 5. Now why am I showing you the constraint? See, while, see, here you will have to make a dp array, here you'll have to make a dp array, and you can see that num and sum, these are the two values that are going to be changed. So this is actually a 2d dp problem, 2d dp problem, correct? So in 2d dp, you're going to take some space of like n square basically, right? So what that n square is, that is k square, which will be 10 raised power 10 in this case. So given the constraint, obviously you cannot use dp approach. So this was the first hint that you have to use greedy in this question, right? Now let's come to the second hint. Let's come to the second hint. let me take another case. Let me take a test case, right? Let me take 81. Let's say case given to be 81. Now, if I just go by intuition, right, my first thought is always, what if I take its square root? It will come to be 9, right? And what if I add 9 number of times, right? And I'm just doing trial and error. But with intuition, I know that obviously I'll go somewhere in the mid, right? And that mid will be from the square root. So from 81, I can see that if I add 9 number of times, I'll get 81, correct? So how many number of operations I have to do to achieve this? So first I'll have to make 1 become 9, right? I'll have to make 1 equal to 9. So I'll have to do 8 operations on like this one, right? So inside of my nums, I'll have one element and I'll keep incrementing it up until it becomes 9. So I'll do 8 operations. And then what I'll do is I'll do another 8 operations to duplicate it. So another 8 operations. So basically you're going to get 18 in this case as an answer. Now what I'll do is I'll try to like deflect from here. I'll try to take 8, right? What if I make 1 become 8, right? So that means to make 1 equal to 8, I'll have to perform 7 number of operations. But how many number of times will I have to add it? Right? Definitely, see, this is 81. So 8 into 10. So I'll have to add 8, 11 number of times. So 11, so basically 10 operations here and 7 operations here. Wait, this is actually 16. Sorry. This is 16. Okay, so 10 operations here, 7 operations here. How many number of operations? 17 number of operations. But I can see that 16 is less than 17. Okay, what if I take 10? What if I deflect from here and take 10? Okay, so if I take 10, obviously to make 1 equal to 10, I'll have to perform 9 number of operations. Then how many number of times I'll have to add 10? So definitely I'll have to add 10, again 9 number of times, because 10 into 8 is going to give me 80. So that is adding 10 8 times is going to give me 80. So I'll have to add 10 9 times. So as to get 90, which is greater than 81, right? So I have 9 number of operations here and 8 number of operations here. So again, you can see 9 plus 8 is going to be 17. Now I can see that what is happening is that it is at the square root where I'm going to get the minimum answer, right? See, the first hint we understood from the constraint, right? It is very important to see the constraint always. Like I also made this mistake and I actually implemented DP, but I got MLE, right? Memory limit exceeding. Then I saw the constraint and saw that it is way large, right? So please see constraint, right? So the first observation here was that you had to see the constraint, right? If there was no issue with this constraint, definitely DP solution was going to be accepted. See, this was the first observation. The second observation was to see what's actually written in the question. So it's written that your sum can be greater than or equal. It's written it can be greater than or equal. It is not exactly k or anything like that. So when it's exactly k, then definitely you will have to go with a DP kind of an approach. But when it is greater than or equal to k, then that means even if I keep adding like the elements that I have, in order to minimize, I can like make the sum greater than k also, right? So that doesn't matter. So that means I can do like absolutely anything. So that is the intuition to like first increment the value and then duplicating it. Otherwise we would have to there could have been the case like you would have been adding values like so, right? That all the values in your array are not equal. That was also the case, and that those choices will be included inside of your DP solution, right? But here in this solution, what I'm doing is I'm first incrementing the value and then I am duplicating it. And the intuition lies here. That first thing was to see the constraint. So here only the DP solution could have gotten eliminated. The second was to see this, right? So both of these observations were very important in this question. And if you observe these two, I hope you I think you would have solved it. But anyways, let us see. So what we are basically trying to do is we are trying to calculate the square root. Now for perfect squares, the solution is quite straightforward. Take the square root. So increment 1 until you reach that square root, right? Square root of this number, let's say x. And also how many number of times you have to add it. you have to add it x minus 1 number of times, right? That is, x is the square root that I'm considering. All right, so for perfect square, it's very easy. Now let us see for non-perfect square numbers, how are we going to arrive at the solution, right? Is square root there also relevant? Okay, let us see. So for 11, let us see, right? So here I can have two cases, right? See, I'm going to consider only integer values here, right? So with 11, the square root is going to be 3 point something. So if it's 3 point something, either I can, choose to have my array elements equal to 3 and then duplicate them, or I can choose to have array elements as 4 and then duplicate them, right? These are the choices that I can have for non-perfect square numbers. So let us go ahead with 3. If I have 3, then to make 3, I'll have to perform two operations. Then plus, how many number of times will I have to add 3? I will have to add 3 4 number of times, which is basically 3 number of operations. Okay, let us go ahead with 4. Let us go ahead with 4. So if I have 4, then how many number of operations I have to do? So to make 4, I'll have to do 3 number of operations, right? And I have to add 4 3 number of times, which makes, see, 4 I already have, so I have to add 4 2 number of times. So basically here you can see, here also you've got 5 and here also you've got 5. But you can go with this option because it's going to be much more safer, right? And it's going to give you correct answer. Reason being that with this, there may be possibility that you're adding this, 2 times more, 3 times more. But with this, right, with the ceil value, this is the floor value, right? And this is the ceil value. If you choose to take the ceil value, then definitely, see, there is only a difference of one operation here when you're incrementing with the value. But how many number of elements after that you have to add? That you can definitely reduce with the ceil operation, right? Because the sum will be much more greater than this, right? So this is what we are going to do. We are going to take the ceil of the square root, right? So square root of k basically. So let us say I save it in x, right? I put this value inside of x. So if I do that, I'll have x. So what are the number of operations that I'm going to get? So I'm going to get x minus 1 number of operations to increment the value, right? Plus, I'll have to do k minus x divided by x, because x is already present inside of my array, right? X is already present inside of my array, right? And I have to divide x, so the remaining sum divided by the number that you have to make that sum, right? To make this sum, how many times you have to divide. Now, in case it is not an integer value, you have to again take its ceil, right? Only then you're going to get the correct number of operations. So that is where, like, this is handy, that you can make the sum greater than or equal to k, but not less than, right? So this is the reason we use greedy approach. And the intuition came from, like, we have to go somewhere in the mid, right? And then definitely we're going to get an answer, correct? So I hope now it's clear to you, like, what we are doing in this question and how it had to be solved and why it is a greedy question. That's very very important, right? So I hope you've understood it. Let us go ahead and quickly see the code. So the code is actually very easy because you have to only return this quantity, right? But let us still go ahead and see. Here I will also show you the DP code that I did. So this is the DP code. I simply memoized it using the DP array, but this was giving memory limit exceeded, right? So it's very important to see the constraints always before attempting the problem so that you can get the hints and work around for greedy problems, right? Because if the constraints were okay, this DP solution would have worked. All right, so yeah, okay. Let us see the solution. For k is equal to 1, definitely you have to return 0 because already you have 1 in your array, so you don't have to perform any number of operations. This is the edge case. After that, simply calculate the ceil of sqrt of k, right? Take the square root and take its ceil. After you take the ceil value, so first this is for incrementing, right? For incrementing the value to x, right? So x minus 1 number of operations are required. Then how many times you have to add it, like how many times you have to duplicate it, that is ceil of float of k minus x divided by float of x, right? So I'm taking ceil because in case this is not an integer value, then definitely I have to like add plus 1. So it's better to take ceil, right? So I hope the solution is clear now.